Good evening, everybody. So my name is Selyunin, as Dima already told. And today I'm gonna show you introduction on photodetectors, like a short introduction, and then we proceed with the practice on SiPM calibration, and then probably if we have enough time, we proceed with the radiation spectrometry using Photomultiplier Tube and sodium iodide scintillation crystal. So, and a few words about the photodetectors. And one of the most widely used photodetectors is Photomultiplier Tubes. A little bit about the principle of work of this detector. So we have vacuum tube. There is a open window which is called photocathode. On the inner part of this glass, so this is the glass, we have thin layer of special material which is called photocathode. When the incident photon hits this surface of this layer, it produces secondary, so the photo effect happening, and then electron emitted from this surface from this surface. So we have electron. So we have incident photon, then we have electron produced by the photo effect, and then we have so-called dynate system. So there is focusing electrode which guide our electron to the multiplication system called dynates. So we have electric field which guide those electrons to the first dynate. So in this first dynate we have there is the work function of this dynate is also very low. So this primary electron can produce secondary electrons. Even normally it produces from 6 even to 12 secondary electrons from first dynate. So the configuration of electric field inside this dynate system then guide those secondary electrons from the first dynate to the second dynate. So we have same amount of secondary electrons here. So for instance, we have one electron on the photocathode. Here we have, let's talk about, let's say 10 secondary electrons. Then we have 100 on the second dynate, and so on. If we have, let's say, 6 stages of such dynate system, in the end we will have 10 to the 6 electrons, which we can, let's say, detect by conventional electronics used in the experiment. So basically we have charge in the end on the output of the PMT. And this charge we can already detect, and then we can say that our PMT detect the incident photon. So those tubes are very sensitive to the light. They can detect, as I said, single photons in very broad wavelength range, let's say starting from 300 nanometers up to 800 nanometers. They can be different sizes, different shapes, and so let's say the biggest one, PMT, has 20-inch diameter photocathode. It's like 50 centimeters tube, and the smallest one they have, let's say, square centimeter surfaces. So, yep. So these few words I already said to you about the photomultiplier tubes. Those devices widely used for, let's say, recent decades, starting from 1930s. And nowadays detector are silicon photomultipliers. What is it? This is a silicon device. So we have silicon substrate. On those substrate we have small cells which is called pixels. And each pixel works as avalanche diode in the so-called Geiger mode. What's the Geiger mode? This is the mode where incident photon, so we have, let's say, incident photon coming to this pixel, and it produces avalanche inside this pixel, which is not which is working in Geiger mode. What does it mean? It means that even if we have few photons coming to the same pixel, the charge from the pixel will be equal. So it's not the proportional mode of the diode. This is the Geiger mode of the diode. So in total, on the surface of SiPM, we have many pixels, and they connected in parallel. So if we have let's say very small light intensities, so our photons will be heated separate individual pixels, and in total charge from the detector will be sum of those output, let's say, charges from individual pixels. So by measuring this pulse, we can say how many photons were incident our surface of the SiPM. The sizes of those pixels is very small. It's micrometer pitch, so normally it's around 10 to, let's say, 100 micrometers pitch. And the number of those pixels can be different, let's say from 1,000 till, I don't know, 50,000 pixels per surface of the SiPM. It depends, of course, of the surface of SiPM, because there can be different surfaces, let's say 1 square millimeter, or the nowadays detector, they have 6 square millimeters. Yep. So here you can see how the view of the SiPM on those photographs, and this is the size. This is the photograph taken from the microscope. Here we can see the different pixels on the surface of that SiPM. You see. So let's today we are gonna try to calibrate the silicon photomultiplier from Hamamatsu company, and this is the SiPM which we are going to use in our setup. This is the pixel size is 50 micrometers. Here we can see the photograph of the SiPM and the photograph of the pixels on those SiPM. So we have surface 6 by 6 millimeters, and in total it's 14,000 pixels on the surface. A little bit about the photo statistics which we're using in our calibration technique. So, there is a fundamental distribution which is called binomial distribution. But when we're talking about the photodetector calibration, Poisson becomes a reality in that case. So Poisson distribution is a partial case of the binomial distribution when we have low probability of events to be happen. And so this is the equation. Please remember this equation, because we are going to use this equation in our calibration method. Please. Here I'm just want to show you how we perform calibration. So on the left hand side you see the picture of Monte Carlo simulation of Poisson distribution, where we have average number of events is average number of X events is 2.07. On the right hand side we are showing the real spectra which we obtained from the silicon photomultiplier. So here you can see that we have same amount of events on those spectra. This is 1 million events. So this is the spectra from silicon photomultiplier, and the statistics, if we want to evaluate the average number of photons. So you see that we have same average estimator is 2.1, and we have for that case 121,000 events in the first peak, which is called pedestal. What is it? Pedestal. This is the signal when we don't have any signal from the SiPM. So basically it's 0 in our case. So when we incident our photons with the light flash, this pedestal, let's say our zero events, allows us to evaluate average number of photons which incident the SiPM surface. I will show you later how to evaluate this. So this is the equation of the Poisson distribution, and here on the right hand side on the bottom you can see the real pulses from the oscilloscope, and here you can see that we have pulses with different amplitudes, right? And so the baseline is this is our 0 or pedestal. The first pulse, this is a pulse which gives us 1 pixel from SiPM, and this is 1 photon detected, 1 photoelectron, sorry, detected. If we have, so we have also double pulse, triple pulse, and so on. So we have 1 photoelectron detected, 2 and 3, and so on. A little bit more about so the previous slide I was showing you the spectrum from the SiPM, from silicon photomultiplier. Here I'm showing the spectrum from conventional vacuum photomultiplier, and the spectra are different because for silicon photomultiplier we have a very good so-called single photoelectron resolution. That's why we can distinguish pulses for 1 photoelectron detected, 2 photoelectron detected, and so on. For PMT, the single photoelectron resolution is worse. In that case, we are obtaining that kind of spectra. But anyway, for that case, for PMT, we also can evaluate the number of pedestal events, so our zeros. And by using the Poisson equation, we can evaluate the average number of photoelectrons in the whole spectra. Does anybody of you knows how to evaluate average those mu value from this equation when we have probability of zeros? So please. Could you, say the formula?
So if you have, so just экспоненты, короче, надо просто посидеть на экспонентах, взять логарифм экспонента и все. Take logarithm from the exponent function.
Okay, but could you let's say write down it on the desk? So we know the probability of zeros. Yep. Right.
We know this.
We know this.
So and to get mu.
Yes, exactly. Yes. It's gonna be different. So, yep, the minus mu, right? This is right. So The average value is minus
so
logarithm
is like minus ln of the probability with zero
yes.
photodetection.
Okay, so how to get the probability of zeros from let's say from this histogram? Maybe you can answer to this question as well.
We can count the times where we don't get any pulses.
Yes. So for instance, we have here 10,000 events, and we have, let's say, 3,000 events in the pedestal. So what's the probability of zeros in that case? So we have in total 10,000.
Well, it's about 2995 division by
divided 10,000. Yeah, right. Exactly. So the probability is 30%, let's say, right?
Yeah.
The 3,000 from 10,000 is 30%. Yes?
Yeah,
this is right?
1,
You're right. So we will use this technique to evaluate the average number for in our practice. So I just want participants to remember this formula because we are going to use it quite frequently soon. So you can have a seat. So yes. So on the next slide, I'm showing you the experimental setup for SiPM practice. So we have a black box here on the table. Inside this black box, we have a silicon photomultiplier and amplifier, which amplifies our signal from the silicon photomultiplier. We have light sources, which is LED, self-stabilized LED, okay? And this, so this is all inside the black box, light tight box. So our LED, so we also have a power supply, which supply our amplifier and the photodetector. And we have ADC, which digitizes our signal from output signal from silicon photomultiplier. And we also have a synchro pulse, which we call trigger signal, which triggers our ADC when we shine with the light flash on the CPM surface. And the data from ADC then is saved on the PC and then processed on the PC. So now we can proceed to the practice, and Alexey is going to show us the screen of the software which allows us to control ADC and save our output signal on the computer. This is the software of ADC, and this ADC software allows us to also see the pulses. So it's like oscilloscope, allows us to see the trigger signal which we're using to trigger the ADC. And here we can see the pulses happening within the width of this, within the trigger signal. And those signals are from silicon photomultiplier. Right now, so we also have LED, as I said you, and we also can adjust the light on this LED. So we also prepared our setup to make it, but to calibrate the silicon photomultiplier, we should work in the so-called single photoelectron mode, where we still can see the zeros on our histogram. So we already set the number of, let's say, photons in the flash on the LED in that regime where we have single photon regime. So, and Alexey is going to save the data right now on the computer. So we are storing 10,000 events at let's say 10,000 pulses, which you can see on the screen on the computer. Then we are going to process them and plot the histogram. So here you can see the process of storing the waveforms. So currently we have stored 7,000 events. So all right, yeah, 10,000 events saved. So now we can proceed. So we have special software which allows us to process those waveforms we stored on the PC. And here Alexei is going to show you the average signal. So we have 10, so in total we have 10,000 events, but to plot the average waveform we are getting from our silicon photomultiplier, we are using 1,000 events, and then we just average them and getting the average waveform. We doing this in order to define the window of integration. So you see those blue lines. So this is the window of integration. After that, we integrate the charge in this window, and then we plot histogram, charge histogram by using those integrals we are getting from the waveforms. Alexei, please. So the data is processing right now. When it will be processed, we will see the spectra, charge spectra we obtained from our silicon photomultiplier. So this is the spectra we get from the silicon photomultiplier right now. So here you can see a few peaks, as I showed you before. So the first peak describes events where we have any signal from CPM. Those second peak, this is signal when only one pixel was fired on the CPM. It means that only one photoelectron was detected, right? And so on. We have third peak where two photoelectrons were detected, and so on. So, yeah.
There's a question. Where is the data coming from?
Those data?
Yes.
So we have waveforms, as we showed before. Did you see the signal on this? You see the signal?
Okay, from a oscilloscope.
It's not a oscilloscope. Those waveforms are saved on the computer. So we have like 10,000 waveforms. And then we have integration window where we evaluate charge from the output of CPM, right? And then those charge we just put in the histogram, and we get this spectrum.
Sasha, and what is the light source?
The light source is LED.
LED.
As I said, yeah, here in the box. And this is self-stabilized LED. What does it mean? It means that it has feedback which allows us to control the intensity of this light flash. It's very stable light flash. The stability is less than 1%. So we have very stable light flash, but very low light flash. So we have single photons coming to the detector. Sometimes it's 0, sometimes it's 1 photon that was detected, sometimes it's 2 photons was detected. And here's the spectra we obtained from the photodetector. So let's try to evaluate the number of average photons in this spectrum. So we already know the formula how to evaluate the average number of photoelectrons in this spectrum. So we have 10,000 events, and Alexei can show us the number of events in the pedestal. Yes. And here we have integral, which shows us the number of events in the pedestal, the first peak or pedestal peak. So we have 4,200 events here. So could you please evaluate the number of average photons in the spectra. So guys, can anybody answer the question regarding the number of average photoelectrons in the spectrum?
94?
Huh?
94?
No.
It's written mean.
Yeah, but this is the mean charge of the, but not number of photoelectrons in the, yeah. So we need average number of photoelectrons in the spectrum. So this is pedestal events, right?
0.9 approximately.
Yeah, should be
86.
it should be a little bit above than 1, I guess. Yeah, you was right. It's almost 0.9. So we have, in average, we have around 1 photoelectrons incident our silicon photomultiplier. So by knowing this, we can calibrate our detector. If we, let's say, want to evaluate or define the detection efficiency of our device, so we can, normally we are using the reference photodetector, which we can compare with our particular photosensor we want to calibrate, and then compare those two average number of photons detected by the photodetectors, reference one and the investigated one. We can conclude what the detection efficiency of those tested detector. So by looking on that spectra, can anybody of you suggest the solution how to evaluate the gain of our detector? So we have 1, 2, 3, like clearly seen peaks, right?
What would be the charge of the single photoelectron peak?
Sorry?
The gain would be the charge of the single photoelectron peak.
Yes. But how evaluate it from this histogram?
Well, 100 is the charge. So one photoelectron peak is the second peak.
Yes.
And his average is about 100. So we have.
You're thinking correctly, but those 100, this is average of whole histogram. It's not like for first peak, right? Yeah, you answered correctly. So we need to evaluate charge, which is describing our second peak, which is 1 photoelectron detected, right? We should find the position of the first of this peak, and then the first peak, which is called pedestal. This is our 0, right? This is let's say our baseline, right? So when we evaluate position of this pedestal, and then we evaluate position of the first peak, which is 1 photoelectron signal. Yeah, we just need to subtract those numbers, and we get the charge which we get from the single pixel. And this is our gain.
It's about 5.
No, I'm not sure. Maybe. If you can, Alexei, can you help us? So we should basically approximate our peaks by Gauss function, get the mean value of those peaks, and then we can evaluate the charge, the gain, sorry. So our software allows us to, so this is a software based on the root package. So we can quite easily approximate those peaks. by Gaussian. So here we have the mean, 95.2. We should remember this number. And then we can fit our second peak, so 95.2. Okay. And here we have 101.146. So we have, what is it? 6, yeah, about 6. So let's say 6, right? 6, and our histogram on the x-axis has picocoulomb. So this is 6 picocoulomb. So can you evaluate from this 6 picocoulomb the gain value?
30,000.
How much?
30,000.
No. So initially we have 1 photoelectron
Yeah.
coming, and then we from
3 times 10 to the 4th.
no.
Pico is minus.
So we have 6 picocoulomb. What's the value? It's
Pico
6,
is minus 15, right?
12.
12.
It's minus 12.
Okay. Sorry. My bad.
What's the charge?
7.
Yeah. So it's roughly 3 10 to the 7, right? Yes. But as I mentioned, in our setup we also have amplifier, which is roughly 50. So we should divide this number to the amplifier amplification factor. So it's going to be 7 or 3 10 to the 7 divided by 50. Yeah, 10 to the 6, even less a bit. So the gain from our CPM is roughly 10 to the 6, let's say. Okay, so now I want to show you the magic. Let's say, so Alexei is going to increase the light intensity a little bit, and then we'll see what's going to happen. Who can guess?
Burn silicon here.
Huh?
You will burn silicon here.
No. So let's say we increase it slightly. Let's say 2 times. What's going to happen then with the spectra we gonna obtain? Yes. Huh?
First or second peak will be the highest.
Yeah. So the events from pedestal and the peaks, they're gonna move on the right, right? And the numbers, not the numbers, only one number. The average number of photons is gonna be changed. So let's have a look on that. So you increase the light, right, Alexei?
Yes. To 600.
Okay. So let's collect the waveforms on the PC. So in the first case, we had roughly 0.9 photoelectrons, and soon we'll define the new number. So the data is stored on the PC. Yeah, on the rest, Она уже открыта, вот это. Она внизу у тебя. So we are about to process the data and then plot the new histogram. So Alexey, could you show us the full spectra? So you see that our second, third, and fourth peak become higher, right? So right now we can evaluate the average number of photoelectrons in our spectra. So Alexey, please show us the first peak. All right, so this is the number we have right now. So please calculate the average number of photoelectrons right now. One point what?
1.47.
1.47. Yeah, I trust you. Yeah. So we increase the light, I would say, 1.5 times, approximately. So what's happened? Yeah.
If I may, question, political question. You use Gauss law to approximate the peak,
Yes,
but
yes.
what is the tail on the left?
Those are noises we have in our setup.
Ah,
So, yeah, we cannot.
maybe some physical source of this?
No physical source. Those are just external noise on the pulses we have
Okay.
from CPM. Huh? Because the ADC we're using, it has slightly declined baseline, and sometimes it has jitter. That's why we have slightly shifted charge on the left-hand side. But this is like specifics of this type of ADC we have right now. So what's going to happen with the gain in that case? We just increase the light. What's happened with the gain? Nothing, right. So to increase the gain, we should increase the supply voltage on the silicon photomultiplier. And so in working in that single photoelectron mode, you can also calibrate the gain. You can just increase the voltage, then obtain the spectra again, define the distance between peaks, and you get the new gain for new voltage. And then you can plot the curve and let's say find the most optimal gain you want to use in your experiment. So this is very convenient way to calibrate detectors by using those Poisson distribution and single photoelectron mode in detector calibration. So I think this is it for silicon photomultiplier practice. So if you have additional questions, please. I'm ready to ask, to answer, sorry.
When I received single photoelectron spectrum from PMT, proper PMT,
Yes.
I received that pedestal and each peaks cross to each other.
Yes.
And we would one form of this.
Yeah, they.
But with CPM
We see separate peak.
yes,
Yes.
separate peaks. Why?
So because of single photoelectron resolution. So in the PMT, when the initial photoelectron are multiplied in the dynode system, right? We have, so let's repeat this process many times. And we have different numbers, right? Because it's not stable. I mean, because the output signal from PMT is very dependent on the amplification on the first dynode. So let's say if we have, but this is a random process, the multiplication of the first dynode. Let's say we have, let's say first case, when we have 10 photoelectrons, secondary photoelectrons for the first dynode. Second time we have, let's say, it's random process, we have 6, right? In the end, we have very big difference in those output signals.
Random processes in each dynode?
Yes, it's random process on each dynode. And in the end, we have very wide spread of the amplitude for, response output for single photoelectron. That's why they were very wide. But in SiPM, we have multiplication inside the silicon. And those amplitudes, they're also slightly varying from one case to another case, but not that high that how it's happening in the PMT. That's why we have the thinner, let's say, amplitude variation for silicon photomultiplier. That's why we can see separate peaks.
So
in PMT, they
vacuum PMT for counts.
In that case, yeah, they're much better. But there are pros and cons for both detectors.
Thank you.
So,
Sasha, my understanding was that in large vacuum PMT you have a large variation because when photon hit different points of the surface, the initial signal can be very different.
initial, you mean?
Yes.
But this is for every PMT.
But in small silicon PM, they are more or less the same because variation is small. The pixel size is small.
Yeah, pixel size and variation amplitude is very small.
Yes.
It's nature of detector, let's say, because it's silicon and we have breakdown voltage. We have, let's say, mostly the same output, not the output, amplification factor from every pixel. That gives us very good the resolution, single photo resolution. In PMT, that they have.
So large PMT has a variety of different incidence angles of the photoelectron to the first dynode, I think.
Yes. This is also affects on this as well. So yes, right. Different angles, different number of secondary electrons there. Yes.
So everything is probably determined by this very first.
No, but for small PMT it's the same. They have better single photo electron resolution. Even on the, could you show the slides with the PMT spectra? We showed. Yes. Please go. Yeah, you see, this spectra was given from small PMT, and here we even can see second photoelectron. But yeah, the single photoelectron resolution is better than for big PMTs. Let's say, I don't know where did you get this one? I think probably this one from the big PMT. But here, for small PMT, yeah, they have better single photoelectron resolution, but not that good as for silicon photomultiplier anyway.
Okay. Other questions?
Yeah, thank you for your speech. And I have some maybe more practice question about which materials is preferred for photocathode.
Photocathode, it depends on, so it depends on your task you want to make. Let's say it depends on the wavelengths basically you want to measure. For different wavelengths region, we need to use slightly different materials for photocathode to get the maximum photon detection efficiency in the wavelength region we want to measure. Those can be different materials. It's Baikal and I forgot, I don't know the English name. Selyunin, Cesi. Sorry, I don't know the name in English. Yeah, but different materials for different cases, for different tasks.
Yeah, and in the photomultiplier we
Yeah.
use что отражается, электроны отражаются от чего, из чего оно сделано.
Do you mean the dynode?
Да.
diodes. Yeah, there are metal plates normally, and there is same as for photodetector. The material not the same, exactly the same, but slightly different because it has higher, even lower work function because we have multiple secondary electrons from diodes, right? It's going to be another material. So we have metal plate and the special material coated on those plates with very low work function that allows us to have many secondary electrons from the diodes.
Yeah, thank you.
So if we put many photomultipliers, we can get the space resolution, yes?
Yes, we can.
And
No, it
but
depends
what
on-
if we get two signals, rather simultaneously? So then we will have 4 points. Well, yeah, 4 points because we have 2 x's and 2 y's.
No. You mean that we can even measure the spatial resolution by using the single silicon photomultiplier? You're thinking that our matrix of pixels can, let's say you the position where the incident photon was.
Yes, if you have many photomultipliers.
If you have many,
Yeah.
yes, we can.
Yes, but when we have many and when we have 2 signals, for
Yes,
example,
yes.
we have 2 points of x and 2 points of y's.
Okay.
But the combinations will be 4 combinations. Not the
Yes.
2
Okay.
points.
Yes.
How to divide? Well, but it should be only 2 points, not 4. Just because we have.
So
2
you have
signals.
let's say this. We have matrix.
Yes, we have a square of points, but
Yes.
only 2 of them from the 4 would be.
So we have, let's say, 1 and 1. We have only one line, right?
No, but how can you distinguish that this x is for those y and those x is for the other y?
So we just need to connect those detectors and make a mapping of the device.
I think I understand your question. So it's usually done not with photomultiplier, but with detector which is sensitive
Yes.
to photons. So you have a layer, say in this direction of strips where you have photons, and then you make a perpendicular layer of strips, and then you read this, and then you get rid of this. So
Yes,
it's not
yes,
with
yes.
Photomultiplier, you get the position of this.
Yeah, but normally when you have, let's say, experiment with the silicon photomultipliers, you connect them separately to, let's say, different channels on ADC, and you know exactly that it was this particular CPM giving you the signal, and then you can directly plot the straight line by knowing this fact.
This is like CCD cameras.
Yes.
You just read every pixel that you need.
Yep.
Okay, other questions? Okay, no, let's continue, right?
So right now, Alexey, please show us the second experimental setup. So here, also on the table, we have setup, which is the drawing shown on the screen. We have photomultiplier tube. Then we have scintillation crystal, which is potassium iodide. And then we will put, in our case, so here I'm showing that we have radioactive source, but in our case we have just conventional fertilizer which we bought in the shop. So we have, where is it? Alexey, please show us. So we have bag of fertilizer. It's potassium fertilizer, and this like potassium fertilizer has potassium 40 inside the bag. So and this is radioactive source, like naturally radioactive source. And then we can put those back on top of the scintillation crystal, and we should see so we will plot the histogram as well, the charge histogram, similar to what we just plot for silicon photomultiplier, and then we will see the peak which is was produced by the potassium 40 in the fertilizer we have in our setup. Then we have same ADC. So I think in our case we won't use the LED because we are limited in time. So and then same procedure. We just store the data from ADC on the computer and then evaluate the charge we get from the PMT and then plot the histogram. So this is the software to supply our PMT. So we are going to apply the 1650 volts to our PMT. So in this case, we are going to work in so-called self-triggering mode. So right now in the ADC software, we just set the threshold. When the signal exceeds this threshold, it triggers the ADC, and then we just store the waveform to the PC. So here you can see the signals from PMT. So this is the light which is coming from the scintillator on the PMT surface and then detected by this photomultiplier tube, and then we see the output signal from the PMT. So Alexei, please save some data on the PC. So we start the data recording on the computer. You see the rate. So our ADC software allows us to see the event rate. So we have roughly, let's say, 20 hertz, 20 events per second recorded on the ADC. So, and now Alexei can try to plot the histogram already. Yeah, on the receiver. So you see that we have much wider pulses with much higher amplitude. This is due to the high amount of the light, and this is like the due to the light pulse shape from the scintillator. They have much wider light shape from the scintillator than our LED produces. So what I'd say, just choose the region of integration. So this is our spectra we get from the PMT. But right now, as you can see, our, let's say, the source is laying is not laying on the crystal, on the scintillation crystal. This is basically the background radiation we just detecting right now. So we have scintillation crystal and all external radiation which enter the, let's say, hitting the scintillation crystal gives us those waveforms. So this is basically the natural radiation background in this room. So we just plotting this, and here you can see already some peak on that position, something between 2000 and 2500. So right now, just remember this spectrum. We are going to obtain our data with our source. Удобрение, fertilizer. Калийное удобрение. So this potassium fertilizer, and it has potassium 40.
In practical, our university practical of nuclear physics, you used to
You're also using this one.
yes.
Yeah, but this is like the source you can buy in the shop, right? The only, I would say. There are some, we also can use, let's say, we also used some kind of welding rods, электроды сварочные. There are thorium welding rods with some percentage of the thorium in the rod, and you can also use those welding rods as the source of the gamma quanta. So the rate is slightly increased because we add additional source. So now the peak is starting to be visible more better than before. So, and we know the energy of this gamma quanta. And the energy is roughly 1.5 MeV. And by using this source, we can calibrate our scale in energy values. So we can calibrate our, let's say, setup in the energy level, and then we can start, let's say, spectrometry. We can even, by using this setup, even evaluate the radiation exposure dose here. Let's say we can evaluate the background or dose, or we can evaluate the dose when we have additional radiation source on top of the scintillator. But so the whole practice on the spectrometry is very long. So I just briefly showing you the main thing we are doing during this practice. If someone wants to get more information how to calculate the exposure dose and different kind of doses, you can, let's say, ask me in the free time, and I can share the document where we have detailed information how to calculate how to make spectrometry measurement and how to evaluate even as a simple example how to evaluate the exposure dose by using those kind of devices like scintillator and PMT. So here we can see that our peaks is very visible, I would say, quite good. And here we know the energy of this particle. This is 1.5 MeV. And so we know the position of pedestal. This is like, you see here there is the setting which is called shift of pedestal. So when we evaluate our measurement, we shift the pedestal to the 100th position on this histogram. So if we fit this peak by Gaussian distribution, we can get the position of this peak, and then we can evaluate the whole charge which is related to this peak, and then we can calibrate our scale in energy values. And then we already can start like our measurement. But normally, when we do measurement, we normally calibrate the scale even in photoelectron values. So we should calibrate the PMT first, then we get charge. So we get the value of the gain value from the single photoelectron spectrum. Then we can evaluate the number of electrons in the whole spectrum, and then we can even define the statistics. Let's say how many photons were detected for that particular energy. So if we spend more time, we can get more better histogram here, but I think that we are already over, right?
Yeah,
so if you have questions regarding those spectrometry practice, you can ask me. Yeah.
Okay, let's first of all thank. I have a question regarding this particular task. So you have a potassium which emit energetic photons like 1 each. Then they release in the crystal some number of photons, and these photons are converted to photoelectrons. So this is what we're measuring in picovolt, right?
Yes.
But I think that if you want to calibrate this is my naive thinking, if I'm wrong, we should take into account the time integration window of your device with respect to the number of counts due to the radioactivity in order to avoid the overlap. Because if, for example, you select a window of 100 nanoseconds, for example, and then we have on average 10 decays in 100 nanoseconds, then we'll have a mistake by factor 10, right?
You mean the cosmic or?
No, from the potassium. So if 10 decays occur in 100 nanoseconds, and we'll then measure, then we'll get wrong the absolute scale.
Yes.
Yes?
Yes, right.
So what are the numbers for the integration window and for the reactivity rate? For the reactivity in Curie?
So we are using, what is it? It's like few hundreds of nanoseconds, and we have 20 hertz, 30 hertz, but this is the coincidence, not very frequent, I would say, and so mostly we have not coincidence signal, I would say, in that case, right?
And what is the radioactivity?
I mean, for that one, it's very small.
It's very small.
Yeah, because the national background was 25 hertz, and it also gives us 5 extra, let's say, events per second for that particular fertilizer. So it's very small number. It's not like hundreds becquerel, let's say.
Yeah. Okay, thank you. So, questions, please.
So, can you turn to the spectrum, the final spectrum?
Yeah.
So I actually photographed the spectrum before you put the fertilizer.
Yeah.
And the distribution was a little lower in this part. Well, considerably lower here.
Okay.
Why the increase?
But so.
And why so sharp decline here?
Они не набрали 10 тысяч.
Yes.
Тоже было ниже, когда они набрали 10 тысяч.
So yeah, right. Probably this is the statistic, different statistics, and we can see like different height of those position, and those are basically Compton scattering, right? Events. This is like the gamma spectrometry.
Not only the peak, but also shoulder.
Yes. Yes. So we just have additional, let's say, events here. Huh? Вот тут? Here?
Yes.
But we should get the better statistic, and then we can conclude on on that, because here it's if we yeah, probably.
Thank you for the question. My question about scintillator Why you use sodium
iodide.
diode scintillation or scintillator? Or what about zinc-MS or some plastic scintillator?
The answer is very easy. We just had that kind of scintillator in hand, and we had the PMT which fits to the crystal we have. So
what will be if you try the plastic scintillation, which have more or less flashing time?
I think the efficiency of sodium iodide is higher for gamma quanta than for plastic scintillator. And so if we have, what do you mean? The light flash is shorter, right?
Yes, shorter.
In that case, nothing. We just plot the same spectrum. That's it.
Okay,
So because we are not using the timing information in that kind of spectrum. So
Any other question, comments? Okay, so it looks that you now know how to work with photomultipliers. Good. Let us thank the lecturers again.